Okay, so this is going to be a quick little 128 equilibrium review. I know a lot of people, when you're coming into 129, you're doing okay with stoichiometry. You got a lot of stoichiometry in high school. 128, you get this equilibrium idea, and you're like, whoa, we had to do that really quick, and we moved on to something else. And then 129, we're doing 9 weeks of equilibrium, and it terrifies people. So let's talk about what we're going to use from 128 and how we're going to use it. So in 128, usually the way we talked about equilibrium was we talked about the enthalpy and the entropy and the temperature. We put these three ideas together, and we said that's going to give us, it gives free energy that's equal to, and this was the energetic way, this was the energy way, to talk about how a reaction would happen. And we talked about being spontaneous or non-spontaneous, and I don't really like that term. That's like a physics term, an energy term. We really want to talk about it as like the energy pushing it towards products or the energy pushing it towards reactants. So that's the kind of energy way to think about it. And we pretty quickly wanted to get away from this in chemistry because we want to talk about the chemicals. And so we had this second way that we could write it. We said delta G is equal to negative RT ln K. And this is the chemical way to talk about it. Where K, I'll even put the subscript EQ on it, it's the equilibrium constant, is going to be the products at equilibrium over the reactants. Now we'll get into specifically what this looks like in a moment. We need some chemical reaction to really talk about what that looks like, where the bracket means concentration. So this step right here, I'm actually going to highlight this with a bright orange arrow. This step here, going from the energy to the chemical system, in my opinion, is one of the most obscured, difficult things that happens in 128. Right? We spend a week or two talking about all these energy considerations, and then we say, or we could do it in terms of chemical considerations. Let's do it in terms of chemical considerations. And we don't get into how these two things really connect to each other, where this equilibrium constant really comes from. It's because there's a bunch of complicated math behind it that that isn't appropriate for a general chemistry class. So we just said, hey, let's take it on faith that we can write equilibrium expressions from the chemical reaction using the coefficients and everything, and we can use that to understand how a chemical reaction is happening. And so let's look at one particular chemical reaction. And I'm going to do a different one than I did earlier. We're going to look at silver chloride dissolving in water. Going to Ag plus aqueous plus Cl minus aqueous. So we've got silver chloride. We're dissolving it in water. It becomes ions in solution. Now, right off the bat, this should be a little bit troublesome to people, because if you remember your solubility rules, we said silver chloride didn't dissolve in water. But what we learned in 128 was there's some energetic argument that says, well, you can't just have zeros here. You can't have zero silver. If there's a chunk of solid in contact with the liquid, with water, there's going to be some amount of silver ions and some amount of chloride ions that end up in solution. And the question really becomes, well, how much? In 127, the solubility rules of it's soluble or insoluble is really kind of a shortcut for mostly soluble or mostly insoluble. And now that we have this energetic consideration, more importantly, we have this equilibrium consideration, this KEQ idea, we can start to talk specifically about what is this. I can say it's approximately zero, but the question we want to answer is, what is it really? So in 127, we just said, hey, it's zero. 128, we got into this idea of like, well, it's approximately 0, but what is it really, taking these energetic considerations into account? We would write this down as some KEQ expression, and we would write it down as the Ag plus concentration times the Cl minus concentration, and we wouldn't divide it by anything, right? We wouldn't divide it by the solid. There are two things that we leave out of in this situation. We leave out the solids and the pure liquids. And this gets into the deeper conceptualization of what the equilibrium constant is trying to communicate, what it's trying to show. So when if we looked at this in terms of having a beaker with some water in it, and we have some amount of solid piled at the bottom. The equilibrium point, most of us think of the equilibrium point as this point where nothing is happening. It's where there's nothing obviously happening. Like on the human scale, we don't see anything happening. But on the chemical scale, there's still some exchange happening. What's happening with equilibrium is the silver ions and the chloride ions are breaking apart as fast as they're coming back together. So every bit of solid that forms, an equal bit of solid dissolves. And there's this balance between the solid forming and the solid dissolving, and the solid forming and solid dissolving. That's the equilibrium. When we look at it, it just looks like a chunk of solid sitting there. So it looks like nothing is happening to us, but there's still some exchange of chemical compounds happening between the solid and the solution. Now, since the solid, every bit of solid dissolving is going into solution, and every bit of ions precipitating is going to the solid, there's this equal opposite effect, and we could either look at we're just going to look at the solution. And so we're going to consider the concentration of ions in solution. So we're not going to consider the solid. Also, if you think about it, how do you write down the concentration of the solid? We need a mixture in order to write down a concentration. That's why we don't do pure liquids either. Pure liquids don't technically have a concentration, so we're not going to worry about that. So we just get the silver concentration of ions in solution times the chloride concentration of ions in solution. That gives us our equilibrium constant. Now, this equilibrium constant only has one value. This only happens at some equilibrium value. And for this particular reaction, it happens to be 1.8. I just looked it up. It's on your equation sheet. Ends up being 1.8 times 10 to the minus 10. The equilibrium constant is only one value. And now, there's a lot of different silver concentrations times chloride concentrations that can give us that value, but those two things multiplied together have to give us that value in order to be at equilibrium. Obvious question becomes, well, what if we're not in equilibrium? Hey, this is a problem we'll do later in the quarter. So what happens if we're not at equilibrium? Well, we come up with another value that we talk about to talk about situations that are not at equilibrium. And it's the reaction quotient. The reaction quotient as the name implies. So we're looking at AgCl solid. Okay, Ag plus Cl minus, both aqueous. States of matter, since we're not including solids or pure liquids, states of matter become really important because they tell us what we include. Our KEQ for this reaction is Ag plus at equilibrium times Cl minus at equilibrium. It has a single value. Our reaction quotient, which we label Q, is Ag plus at any value times Cl minus at any value. And this can be any value. Now what this means for us is we can compare, we can say, well, okay, well if I've got any value, what happens if I'm at some value that is bigger or less than the equilibrium constant? The easy one to consider is we can always have KEQ and Q equal to each other. That's at equilibrium. We can also have KEQ is greater than Q, or we can have KEQ less than Q, right? Those are in terms of math, those are the possibilities we can have. KEQ is equal to Q, KEQ is greater than Q, KEQ is less than Q. This one, this is the situation that we usually dealt with, right? If you think about the previous problem, we were putting it, we had silver chloride, we were putting it into a bucket of water. The silver concentration in a bucket of water is 0. The chloride concentration in a bucket of water is 0. Q is 0. KEQ is greater than 0. This was what we always had in 127 and often in 128. So this is going to be the situation that goes towards products. This situation where KEQ is less than Q, this is a weird situation that we're going to actually deal with more often this quarter. And we're going to have a trick for dealing with it. And that's going to be the situation where we have towards reactants. The easy trick I have for remembering this is that less than sign, you could pretend makes a little arrow that points the direction the reaction goes. The greater than sign makes a little arrow that points the direction the reaction is going to go if you put KEQ up front. If you do Q versus KEQ, it messes everything up. So we've got these different considerations. Again, this situation, this is the one we deal with most often. You've got either one thing or both, one product or both products have 0 concentration. So your Q value ends up having a value of 0. KEQ is always bigger than 0. Sometimes it's really small, like 10 to the minus 32. Still not 0, still bigger than 0. So this is the situation we deal with most of the time, but these other situations happen as well. Question, yeah?
So there's KEQ, but I've also seen I think it was KSP and...
Yes! KSP, KAK. They're different-ish.
Okay.
So let's talk about, and I was trying to think of what I wanted to talk about next. Let's talk about that. So I say towards products and towards reactants. That means we're referring to a particular chemical reaction. Mm-hmm. And the subscripts help us talk about which chemical reaction we're talking about. So for this particular thing, actually, let me swap this out. So for this particular chemical reaction, I'm just going to erase this stuff all the way back up to here. For this particular chemical reaction, I could write it down as a KEQ, but I want to give some hint. Anytime we change subscripts, particularly when we're labeling things, we're trying to give some hint. KEQ is any equilibrium. If I want to give the readers or the people working on the problem a hint that it's specifically a solid dissolving into ions, so you're going to have ions in solution, there's going to be water involved, and there's some solid that we're not involving, we'll give it a KSP. This is when we are looking at the reaction. That is specifically when we are looking at the reaction of solid to ions. So we give this this subscript to kind of give a hint. Then we can also have the Ka, and this is the reaction of how do I want to write this down? Hang on a second. this would be the reaction of, I want to be consistent with my other notes. We're going to have a better way to talk about this, but this is specifically acid giving it H plus to water. There's a particular reaction. When we write K with a subscript A, we're talking about a particular reaction that's going on. Same thing if we want to talk about KW. That's the one that we're going to use a lot. This is the reaction of water. Water reacting with water. I know that sounds weird. We call it the autoionization. The autoionization of water. And we're going to talk about what that means when we start talking about acid-base chemistry, because water mediating our acid-base chemistry is going to be really important. The difference, these are all KEQs. They're all equilibrium constants, but the subscript's trying to point us to a particular chemical reaction that we're talking about. So that way, it's trying to give us a hint. So let's go ahead and ask a particular question about this AgCl situation and figure out how we use this mathematically. So we're going to look at the particular question of what is the concentration of Ag plus and of Cl minus in a saturated water solution. So we're asking for, there's a couple different ways we can think about this. This term saturated comes up pretty often. And that just means we're hitting the maximum of ions in solution. We're hitting the maximum of ions in solution. It's another way of saying equilibrium, essentially. So we want to figure out what's the concentration of Ag plus and of Cl minus in a saturated water solution. So we're starting with water. So if I look at this, I'm going to have my AgCl solid going to Ag plus Cl minus. And if I think about this, initially, I'm not going to worry about the solid. The solid's not going to participate in the equilibrium calculation. It's participating in the process, but we can just look at the solution and get everything we need from there. Initially, in water, there should be no silver concentration. There should be no chloride concentration. Now, whether we put in whether we're just adding silver ions and chloride ions, or if we're throwing in an entire truck, I like to think of it, there's a lot of different ways we can think about it, and we'll do a little bit of that after we calculate this. But I like to think of it, to start, as I throw in a giant chunk of silver chloride. As much of the silver chloride is going to dissolve as possible. We're expecting this to be a small amount because silver chloride is generally insoluble, but let's figure out how much. So initially it's just water. That silver chloride falls in, immediately starts changing the solution. That change is going to be every bit of silver chloride that falls apart puts in one piece of silver ion, puts in one equivalence of silver ions. Every time that silver chloride falls apart, puts in one equivalence of chloride ions. Until, and it'll keep doing that, until we reach equilibrium. So I don't know how big this x is. It's enough to get it to equilibrium. I'm going to have 0 plus x gives me x, right? I'm doing my math in a column. And the same thing here, 0 plus x gives me x. By the end of the first week of class, we'll do problems where you're not doing it in water, you're doing it in different solutions, so those things aren't 0. It gets a little bit trickier, and we learn some ways to deal with it. But right now, we're just doing it in water. We got 0 plus x is x, 0 plus x is x. And then I can just set up my numbers to figure out the equilibrium. I'm going to have a KSP, right? And I could put this as KQ, but we've talked about this, so we'll do it as KSP, is equal to X times X. And that's going to be, and I'm going to, the equilibrium, let me write this a little different. This is going to be KEQ is equal to the AG plus. I'm going to write that same thing again in just a moment. EQ times the CL minus EQ, which we can translate all of this to say, well, this is particularly a solubility reaction. The concentration of silver at equilibrium is this value X. The concentration of chloride at equilibrium is this value X. And I can plug in the number for KSP, which is 1.8 times 10 to the minus 10 equal to X squared. This is the equilibrium expression. That is the equilibrium value. Right? The specific number for it versus the conceptual how we write it in terms of concentrations. I can then solve for my X here, taking the square root. I've got the answer to this someplace already. 1.34 times 10 to the minus 5. This value, 1.34 times 10 to the minus 5, that is the concentration of silver ions at the point of saturation. That is the concentration of chloride ions at saturation in water. So I could think about this multiple ways, what I was talking about before we had these numbers. I could achieve this by throwing in a giant chunk of silver chloride, and the giant chunk of silver chloride will dissolve a little bit until it hits those concentrations. Or I could set this up where I've got my bucket of pure water, and I put in the exact right amount of silver ions and the exact right amount of chloride ions. There's no solid in there, but I've saturated my solution where any more silver or any more chloride would upset that, and it would start to form solid. Another thing we did when we had these saturated solutions, again, this equilibrium situation, where when we hit this value for silver and chloride, we're at equilibrium in solution. In 128, one of the things we started to talk about was, what if we disturbed the equilibrium by adding extra Cl minus, or adding extra Ag plus, or doing something to remove Ag plus from solution, or remove Cl minus from solution? That was thought about in terms of this thing called the Le Chatelier's principle, which is the conceptual idea of it, which says, anytime we disturb a system that's at equilibrium, nature will reestablish equilibrium. Why does Le Chatelier's principle work? Gibbs free energy, enthalpy, entropy, temperature, right? There's an energetic drive behind all of this. We're just going to focus on it in terms of the chemical thinking, the KEQ value. Questions before I do one more problem? Good. Okay. So the other problem, I want to do these ones that have 1-to-1 mole ratios, like when you look up examples of this, one of my problems with textbooks and like video help things online, they only do like the easy 1-to-1 mole ratio, everything, and everyone's like, oh, I can do that. And as soon as you do a 2-to-1 ratio or like a 1-to-3 ratio, it's like a mess. So let's go ahead and look at a different chemical reaction and ask the same question with something that's not a 1-to-1 ratio. So let's go ahead and look at magnesium. Let's look at magnesium chloride. Oh wait, no, not magnesium chloride. This is what I get for trying to change what I want to do in the middle of doing something. Magnesium chloride is super soluble. That would be a bad example. I mean, I just don't have the value for it handy. Let's do magnesium hydroxide, the example that I had already had planned. Magnesium hydroxide is a solid. If we put that solid into water, it will dissolve into magnesium 2+ and OH minus, 2OH minus. How much it dissolves now becomes the question, right? We just saw this silver chloride where it was like silver chloride dissolves, barely dissolves. So our 127 definition of soluble and insoluble is really not detailed enough, right? It was mostly soluble, mostly insoluble, and we can find like what's the actual value of it. So we're going to find our magnesium 2 plus concentration and our OH minus concentration.
What is the reason that like things that are like very insoluble that they dissolve at all? Like, why does that happen?
So it's the energy part of it, right?
Okay.
When we look at this chemical reaction, when I look at this magnesium hydroxide, there's some lattice enthalpy, hydration enthalpy. What was it? Hydration enthalpy, lattice enthalpy, solution enthalpy. Do you remember that from 128?
Yeah.
That's the answer.
Okay.
We're just going to say there's some energetic argument, right?
Okay.
128 got into some details of the way that the magnesium and the hydroxides are interacting with each other. This is an ionic bond between the magnesium and the hydroxide, and there's some energy associated with that ionic bond. And to the point where there's like ionic bonding on top of ionic bonding making a crystal lattice. Versus over here, there's some ion-dipole interaction between the magnesium and the water, and some ion-dipole interaction between the hydroxides and the water. And the energy of this interaction is greater than or less than the energy of this interaction. There's still some energy to that interaction, so it'll happen, and how much it happens depends on those differences of those enthalpies and the entropy and the temperature at which we're doing it, all of which we wrap up into just a value we call K.
Right. Okay.
And so we look at it and we say, well, there's an equilibrium constant that captures all of those energetic arguments and just says, it happens a little bit. So if we set this up, I'm going to change colors so we know we're working on a different problem. I've got this set up, magnesium hydroxide, solid, dissolves energetically because of all that into H2O, into magnesium 2 plus aqueous, plus our 2 OH minus aqueous. My initial, since I'm still doing this in pure water, I start with zeros for my magnesium, 0 for my hydroxide. The change, as this solid dissolves, or as I pour these ions into solution, I'm increasing the amount of magnesium, and I'm increasing the amount of hydroxide. It's a +1 because every magnesium hydroxide that dissolves makes 1 magnesium. Every magnesium hydroxide that dissolves makes 2 hydroxides. And then I'm going to do this until I hit some equilibrium point. I'm going to have 0 plus x is x, 0 plus 2x is 2x. And I can set this up. I'm going to have my KEQ is going to be products over reactants. That's going to be the magnesium 2 plus, the OH minus, squared. This square comes from the coefficient. The fact that I've got that 2 in front. Now you'll notice here that 2, that molar coefficient, has 2 effects. It has an effect on the equilibrium expression because there's some energetic argument that's going on there with that natural log of KEQ and the natural log of all the energies. And that's why it becomes a coefficient, because natural logs and inverse natural logs. And it also comes in when we look at our stoichiometry and the fact that magnesium hydroxide falls apart into 2 hydroxides. So that coefficient plays 2 different roles, an energetic role and a stoichiometric role. We can go ahead and take this and we can say, look, I can go ahead and call this specifically a KSP, because this is a particular, it's a solid going into ions. That is the S, that's what solubility product is referring to this particular reaction. Then I can go ahead and say my KSP value for this, again, I've got it down already, is 6.3 times 10 to the minus, well, let me, yeah, I got space here, 6.3 times 10 to the minus 10, and that's going to be equal to my magnesium concentration times my hydroxide concentration squared. So notice again that 2 is being used in multiple ways. The stoichiometric and the energetic. So I'm going to end up with 6.3 times 10 to the minus 10 is equal to 4x cubed. This 2x quantity squared gets us 4x squared times x gets us 4x cubed. I can then solve for my x value, rearranging this, doing some solving. I already plugged it into the calculator a minute ago. I get 5.4 times 10 to the minus 4. And that would be my concentration of magnesium ions at equilibrium, the saturated value for this particular problem. In order to get the hydroxide concentration, I need to solve for that 2x, which would just be that number times 2, 1.08 times 10 to the minus 3 molarity. That's going to be my hydroxide concentration, the 2x. Particularly 2x because of the way we set up the problem. And we find that for these solubility problems, this is usually how we set it up. We set it up so it's in terms of this x value is in terms of the solid disassociating. Even though, we're not looking at the solid, we still want to understand how the solid relates to this. And then we're only really looking at the ions that end up in solution. So even though we don't consider the solid is still playing a role in some way. And this is kind of most of what we did in 128. 128, we also talked a little bit about acid-base equilibria or acid equilibrium in water. It's essentially the same type of calculation. We only did really simple calculations with it. We're going to do some of this in our next class, depending on when you're watching this video. Maybe we already did it. We do this like the first 2 days of the quarter. And then we immediately start going into, well, what happens if we do weird situations? What happens if these are not zero? What happens if we disturb the equilibrium in particular ways? By adding, like this is a really easy one to disturb. We can remove hydroxide by adding acid into the water. If we add acid into the water, the hydroxide reacts away, and now we've disturbed equilibrium. How does this system respond? In the past, 128, we just did it as like Le Chatelier's principle. You remove a product, more products have to form. 129, we can calculate the stoichiometry of how much acid did you react, how much hydroxide did you remove, and how much does this system need to respond to reach the new equilibrium, and what are the new equilibrium values. We can finally put numbers to all of that. And that's what we're going to do this course. So hopefully that's enough to kind of get your brain remembering some of this. If you were worried about equilibrium because you were terrified of like Gibbs free energy, enthalpy, and entropy, we're mostly avoiding that. We're mostly doing equilibrium table calculations, what some people refer to as ice table calculations, which I stopped doing in 128 because you also have all those melting ice, forming ice problems. And so when I said ice tables, people were like, oh, I thought we were doing something like equilibrium tables.